All right, welcome back to the Chapter 2.5 video lecture series. And we finished on this slide, but as a quick review, we're looking at linear correlation between two variables. The variable is r, and r is defined to always be between -1 and 1. And the sign of r indicates the direction of association. So if r is positive, then we have positive association. The scatter plot will have a general upward trend. If we have r is negative, then we're going to have a negative slope or a negative correlation, downward trend. And if r is about 0, then it's just kind of chaos or random or a shotgun blast. The closer r is to plus or minus 1, the stronger the linear correlation. R has no units, does not depend on the units of either variable. And I didn't mention this last time, but if we switch the variables, if you were to change x and y, we would get the same exact correlation. So it doesn't matter which variable you pick to be x and which variable you pick to be y. That will change the line of best fit, but we'll talk about that when we cover Chapter 2.6. So let's look at a couple examples. We're just looking at this scatter plot. We just say the correlation is closest to -1, -0.5, 0, 1/2, or 2. Feel free to pause and make a guess. Hopefully you immediately crossed off 2. Correlation is never greater than 1. And hopefully you crossed off 1/2. If you could see this, the general trend is negative. The more we go on the x-axis, the lower we go on the y-axis. And -1 is perfect correlation, meaning all these dots will go on one line, so it can't be -1. So it has to be -1/2 out of these options at least. What if we take page number versus fuel capacity? We talked about this a couple slides ago. Hopefully this is about 0. There's really no correlation. Or you can think about if you could just draw a flat line between your data, that really means no correlation. And that also means a flat line has 0 slope. Think like that. All right, here's kind of just an interesting graph. Again, this data comes from I think the 2015 NFL season, so it's a couple years old. But there's a rating on the malevolence of the uniform. And then here is a z-score, just standardized for penalty yards. Basically, how many penalty yards a team gets over each game and over a full season. And I guess those of you that follow football, what do you think? We have an outlier of the most malevolent uniform and then the least malevolent uniform. Interesting to see if you can guess those. Well, here with this data, we get R about 0.43. So we have a positive correlation. I would say a weak to moderate to weak positive correlation. It looks like all the middle data points are just scattered. Then just to note, the most malevolent is the Raider mascot, and the least malevolent, I actually got this one. I got this question from the textbook. I didn't get this value down here. That's the Dolphins. I guess the Dolphins are not very malevolent. But I want to show this graphic because what happens, I think these are fairly clear outliers here, the rest, apart from the rest of the data. What if we remove them? So here's the same data, but now we're removing the 2 outliers, the Dolphins and Raiders, and now the correlation got very, very close to 0. Go back to the last one. With those 2 dots, that makes the correlation moderate to weak. Get rid of those 2 outliers, and the correlation is almost nil. We almost lose all the correlation. All right, so some correlation cautions. Correlation can be heavily affected by outliers. Always plot your data. So you want to plot your data, and we'll go over some exercises where you take out the outliers and leave them in and see how correlation changes. R equals 0, or approximately 0, means there's little to no linear association. But the variables could definitely still be associated another way. So you always want to plot your data and analyze your data. And I have an example here. I teach a business calculus class. So I look at a lot of like revenue functions that plot revenue. And here you see I've got just 6 data points of various revenues. Units sold in revenue. And notice right here, we've got this upward trend and downward trend. And the correlation given is 0.3748. So I'd say that's moderate to very weak correlation. But hopefully, I've taken a math class before, you might want to think, well, it looks like these points, these scatter points, fit a different type of curve. And we won't do this in this class, but I want to show you we could create a polynomial. This would be a quadratic correlation, like x squared or minus x squared. This type of graph. So we have a quadratic correlation. And if you calculate r squared for positive correlation, it might be hard to see. Here we get the correlation to be close to 1. So this right here is, right here, quadratic correlation. So we won't be covering this in this class. We're going to stick with linear. But I just want to give one example where even though the line doesn't fit the data very well, there could still be a strong correlation just via a quadratic curve. All right, one other thing to look at. Oh, sorry, I need to fix my graph here. But here we plot TVs per 1,000 people in various countries, and then life expectancy. And here R equals 0.7. I would say this is a moderate to strong positive correlation. Generally, the more TVs per capita, the higher the life expectancy gets. And like I said before, this number here is pure mathematics. This is a mathematical construct that, we have computers to calculate this number for us. But it's pure mathematics. I think almost any human could look at this and say, well, we don't want to give more TVs to countries. That's not going to increase life expectancy. We actually looked at this example before, and the confounding variable here, or one of the main confounding variables, would be income or wealth. Right? Generally, it's probably more wealth a country has, the higher the life expectancy, and that's confounding this TVs per capita. So that goes back into correlation does not imply causation. All right, as a summary, we looked at scatter plots for visualization, and then we looked at correlation. I want to go back just very briefly to that idea of correlation does not imply causation, because there's a spurious correlation. Let me see now that this fit the window so you guys can see what I'm looking at. So this was a statistician kind of came up with this web page. Zoom in here. I think it's fairly entertaining. Just to kind of show the that correlation versus causation issue. Now ridiculous book. So here we're looking at U.S. spending on science, space, technology, suicides by hanging, strangulation, and suffocation. Has a correlation, as you can see here, of almost 1.997. See. So strong correlation between these, but I think anyone reasonable would say that there's no causation between what the U.S. spends on science and space versus suicides by hanging. What this person did was Tyler Vigan took snapshots, basically kind of finding data sets to force high correlation. Number of people who drowned by falling into a pool correlates with films Nicolas Cage appears in. Again, this would be moderate to strong, 0.66. But I would argue this is probably no real causation connection between these two, unless you really, really hate Nicolas Cage. I just love this example. Per capita cheese consumption has a strong correlation with the number of people who died by becoming tangled in their bed sheets. When it's amazing how many people die in this situation. It's kind of nuts. There's probably some drug and alcohol use involved in here. I would guess. And maybe you want to think that if you just eat pounds of cheese, then you die because you can't get out of your bed sheets. But generally, I think most people would say that there's really no causation between these two. A very strong mathematical correlation. And if you just Google spurious correlation, there's a bunch on here. Divorce rate in Maine, consumption of margarine, age of Miss America, murders by steam, hot vapors, and hot objects. Not too many murders, luckily, in this case, but very strong correlation between the age of the Miss America winner. This one, maybe you can argue there is a causation. Total revenue generated by arcades and computer science doctorates. So sociology doctorates versus worldwide commercial space launches. Hopefully you get the idea here. Correlation is pure mathematics. It is absolutely not the same thing as causation. If there's one thing you take from this class, 5 years from now, that correlation is not the same as causation, I will be a happy instructor.